Hi, I'm Dr. Macy Levan, and I'm here with Dr. Weiss. And would you just take a couple moments to introduce yourself and tell everybody about what you do and why you're excited to go to TTS 2026 in Sydney, Australia?
I'm Tony Weiss from the University of Sydney, where I'm the McCaughey Chair in Biochemistry and also NHMRC Leadership Fellow at the University of Sydney. We have spent decades understanding how the body builds its most flexible tissues. I think our work will be very exciting for the TTS 2026 community because the tipping point in the field isn't just simply about growing an organ in the lab. It's also about using synthetic biology to create materials that the body actually recognizes as its own. My talk will focus on how we use the building blocks of connective tissue, of human elastin, to program tissue repair. That'll move us away from the temporary patches and towards permanent functional regeneration. If you want to see how molecular biochemistry is becoming a surgical reality, you won't want to miss this session.
So, I've got a couple questions for you. What has changed in regenerative medicine over the past decade that makes transplantation scientists pay attention now? And are we moving closer to bioengineered grafts that meaningfully enhance or replace traditional transplantation?
So I think the big picture really is that we are moving a lot from inert materials. These are materials that are things like plastics or metals and so forth that are commonly used for transplantation systems to instructive materials. These are really interacting with cells. And so there's a convergence happening right now. That convergence is that we need to have a crosstalk between cells, particularly pluripotent stem cells, and those cells interact with their environment. The classical environment being the connective tissue, if you like, the scaffold. And that provides the house for cells that tells those cells how to behave. Now, historically, we've seen that these plastics, these polymers, these metals as providing a fairly passive environment. But rather now the shift is towards an instructive environment where these cells interact with their environment. And that's one of the things we're learning a lot about and why I think this field is so exciting. It's this move away from just simply seeing this as cells alone to the environment the cells sit within. So what about the scientific and translational advances, how they're being seen? From my lab's perspective, we're using elastin, which is the body's soft elastic material. Elastin is basically what gives a range of tissues, organs, their functionality from an elastic perspective. Elastin is what gives our heart, our lung, our skin its snap. And without that elastin, a transplant or repair is basically just a static fix. We have unlocked the way to manufacture human identical tropoelastin, which is the building block of elastin. We have learned about the assembly rules and how it interacts biologically, and that has allowed us to build grafts that grow and stretch with the patient, which I think is incredibly powerful and exciting. From a scalability perspective, there is a barrier. Often people talk about the scalability barrier. And I have been able to found the company, take my technology through from the bench to bedside. That technology has been now used in many patients. And that transition from bench to bedside isn't just simply hypothetical. It has become a reality of taking these elastin or tropoelastin-based materials through. So the challenge isn't just simply making something work within a lab, but making it pure, making it deliverable, making it mass producible. And this is something that I think is also very, very important in the field. How do we provide the framework, the environment for these pluripotent stem cells or other types of cells to interact with in a three-dimensional environment that replicates the functionality of human tissue? So in that respect, we come to the question of future directions. The future directions are manifold, but I think there are two particular ones I'd really like to focus on. One of these is a shift in the mindset. I think that researchers and surgeons need to start thinking of themselves as not just simply people who pick up an object and place it directly, such as an organ, directly into patients, but rather we need to start thinking of ourselves as regenerative architects. And as regenerative architects, we then start to realize that we are building and constructing a 3D environment that is very functional and works extremely well. So, thinking of that term regenerative architects, which I think is a great term to contemplate, we can think of the present day, the mindset shift as I describe it, but we can also think about things like a 10-year vision, if you like. And I would encourage you to imagine off the shelf bioengineered constructs, organs that don't just simply consist of bioengineered vascular grafts or skin substitutes, where we're heading at the moment, but rather an integrated three-dimensional reality that brings different types of cells together that make a fully functional organ system that is fully vascularized, that uses this kind of regenerative architecture to be able to build things that can basically be fully constructed in the lab, well beyond the days of basically using bioprinting methodology. Rather, we're using an instructive conversation between the environment and the cells that sit within them. And the resulting constructs then can be integrated seamlessly without the risk of rejection that is seen in traditional transplants, and can address the big gap about materials that can be used, organs that can be used that are fully compatible within a biological system. And I would encourage you to envision a world 10 years from now where we no longer need to contemplate the use of rejection drugs as a way of being able to allow these fully integrated constructs to be able to be used with patients.
That was wonderful. Great information. Really appreciate you giving me that thorough look at your work and what you think is important for the future. So, kind of the last area that I want to talk with you about is TTS 2026. And what are you excited about seeing in terms of papers and abstract submissions in the area of regenerative medicine and biomaterials and stem cell biology and translational transplantation?
So I am particularly excited and will be looking out for those papers, those presentations that really address the interactional interface. How do cells speak to their environment? How does the environment change the behavior of cells? And this is moving well beyond just simply things like mechanotransduction and other interactions. We need to think in three dimensions, but over time as well. And this concept of both space and time is something that biology's been using for many millions of years. And we need to think about that in the same way, biologically and medically as well. So looking for those kind of interfaces, looking for the instructive interface between the living systems themselves and the environment that they in turn speak to, I think will be particularly exciting and predictive of where the field will be going in the future.
Well, thank you so much. You've given us so much great information to look forward to TTS 2026 in Sydney, and I thank you so very much for your time.